Now that we've had a little review of inverse functions, I'd like to talk about y equals the sine of x. I'd be interested in finding the inverse function to the sine of x. However, I would like to point out that if you take a look at the graph of the sine function, you'll notice that it fails the horizontal line test really badly. That's because anytime I create a horizontal line, it is going to hit this graph an infinite number of times if we were to extend this out infinitely in both directions. So in response, what we're going to do is restrict the domain. We're going to be doing this process for all 6 of our trigonometric functions, and the domain restriction is going to work with a couple of guiding principles. We're going to make it a point to stay close to x equals 0. So on the unit circle, expect to see a lot of angles that are around quadrant 1. Additionally, we're going to connect a minimum to a maximum. And that's it. If I were to go beyond a minimum, this thing would once again fail the horizontal line test, and if I were to go beyond a maximum, it would once again fail the horizontal line test. So starting at x equals 0, I'm going to go to the left until I arrive at a local minimum. I'm going to go to the right until I arrive at a local maximum. This is the only piece of the graph that I want to use. Now the corresponding x values for that local minimum and that local maximum occur at pi over 2 and negative pi over 2. Corresponding y values are negative 1 and positive 1. So we restrict the domain in the following fashion. Y equals the sine of x, and x is going to be between negative pi over 2 and positive pi over 2. So the only piece of the graph that we're going to see will connect negative pi over 2 to positive pi over 2. Having restricted the domain, we have now created a one-to-one function. Now, frequently this shows up on the unit circle as well. Now, as far as the unit circle is concerned, we're going to be defining angles in a slightly different fashion. Normally, as we make our way around the unit circle, in terms of radian measures, we would label these as 0, pi over 2, and pi. Then we would go on to label this as 3 pi over 2. But angles are now going to start at 0 and go in the the clockwise fashion. So rather than labeling this angle as 3 pi over 2, I'm going to label it as negative pi over 2. So the angles that will work for the restriction for the sine of x are going to be all of the angles that are in quadrants 1 and 4, connecting negative pi over 2 to positive pi over 2. This allows us to define our inverse sine function. The inverse sine uses the following notation. It uses the same inverse symbol that we see associated with inverse functions. However, because that can be a little bit confusing, because this looks an awful lot like a superscript to mean the power of, it really doesn't mean that. So occasionally we refer to it as the arc sine function. So saying that y equals the arc sine or inverse sine of x is equivalent to saying the following. The sine of y is equal to x, with the following restrictions. Y is now serving as our angle. Our angle is supposed to be between negative pi over 2 and positive pi over 2. The corresponding ratio is going to be between negative 1 and positive 1. So to evaluate an arc sine is to say, can you identify the angle that has this ratio as its sine, as long as the angle is between negative pi over 2 and positive pi over 2. So for some examples, if I were to ask for the arc sine of 1/2, I'd be asking what angle within our restriction on the unit circle from negative pi over 2 to positive pi over 2 has a sine that is equal to 1/2. Now that means that on the unit circle, I would be looking for the angle where the y-coordinate is equal to 1/2. That angle can be identified as pi over 6. And this is because the sine of pi over 6 is equal to 1/2, and pi over 6 is within the appropriate restriction, which is between negative pi over 2 and positive pi over 2. If I were interested in finding the inverse sine of negative root 2 over 2, setting it up once again, our restriction goes from negative pi over 2 to positive pi over 2. This time, because the ratio is negative, I'll be interested in finding the angle that is in the fourth quadrant. So somewhere in the fourth quadrant, you'll find an angle whose y-coordinate is negative root 2 over 2. That's the angle that I'm looking for. Now normally on the unit circle, we would probably identify that angle as being 7 pi over 4. But 7 pi over 4 is referring to the following angle, and that's not the angle that I'm looking for. I am looking for this angle. Now that is coterminal to 7 pi over 4, so if you identified it as 7 pi over 4, you could always subtract a full revolution from it. You'll also notice that there's symmetry with the first quadrant. So if you can identify the angle in the first quadrant whose sign is positive root 2 over 2, go ahead and tag on a negative sign and you'll have your answer. So once again, this is because the sine of negative pi over 4 is equal to negative root 2 over 2, and negative pi over 4 is in the appropriate restriction, as being between negative pi over 2 and positive pi over 2. Some other common ones that you'll see from time to time, if I were looking for the arc sine of 1, I would be talking about pi over 2, because the sine of pi over 2 is equal to 1. The arc sine of 0 is equal to 0 due to the fact that the sine of 0 is equal to 0. And the arc sine of negative 1 is going to be negative pi over 2. Now with those things in mind, if I were to ask for the arc sine of something outside of the domain of negative 1 to positive 1, you could tell me a very easy answer after that. That very easy answer would be DNE, which stands for does not exist. You could also call it undefined. That would work as well. So do keep in mind the domain restriction that we had associated with the inverse sine. If you have any ratio that's outside of negative 1 to 1, the arc sine of that ratio is undefined, or does not exist.